I would like to thank and Yang providing me this opportunity. This presentation is about our research work on data centers waste heat for building space heating. Before diving into technical details, I would like to outline some outcomes of this work. So this work can achieve complete waste heat recovery. Importantly, there is no need for heat pumps, which are commonly used. Therefore, investment and carbon emissions are minimum with payback time less than 1 year. So our aim is to, it's very short, this payback time. Our aim is to achieve low in investment for practical applications. We'll see. Let me start with background information. The exponential growth in internet has led to a dramatic increase in data centers' energy use and carbon emission. The left graph from IEA showed that in 2020, the emission was comparable to the world's airline industry with very high projected growth rate. The emission must be cut. The right graph illustrates 3 primary carbon reduction methods, and waste heat reuse is one of them that particularly promising due to the nature of IT system, because over 90% of the energy consumed by IT is converted into heat, and at the same time, IT requires cooling for function. One of our studies indicate that in theory, over 97% of waste heat can be utilized. The potential is huge. However, practical applications are limited due to various challenges. For example, the waste heat is low-grade heat that is not easily to be applied to traditional thermodynamic processes. Nevertheless, there are few applications targeting district heating network, mainly in Finland and Sweden. There are compelling reasons because both buildings and data centers are significant contributors to carbon emissions. Reusing waste heat from data center in district heating can significantly reduce carbon emissions for both sectors. It's like sector coupling. For example, Finland aims at carbon neutrality by 2035, very soon, the world's first carbon neutral welfare society. So the country is under big pressure. Fortunately, our district heating network are very advanced, exceeding 90% adoption rate in big cities. Therefore, many IT companies utilize waste heat to district heating. Small data center companies advised to use waste heat to heat nearby buildings. There are many large-scale applications, for example, already.
Sorry, Professor Zulu, just a second. I think it's a song. Really how to unmute somehow. Can you unmute yourself, please? Sorry, couldn't hear you. Probably how to unmute yourself.
Oh, sorry.
Yeah, it's okay now. Thank you.
Sorry, should I, is it, how is it possible? Is unmute? So should I start
Yeah.
from beginning?
No, it's only last minutes or so.
The
It's
last,
okay.
okay.
Yeah, yeah.
No, it's okay.
Yeah,
All right.
it's okay now. Thank you.
Okay. So,
Sorry.
yes, no, sorry. Finland aimed at carbon neutrality by 2035, the world's first carbon neutral welfare society. It's very soon. So the country faces big pressure. Fortunately, our district heating network are very advanced, exceeding 90% adoption rates in big cities. Therefore, many IT companies utilize waste heat to district heating network. Small data centers are advised to utilize waste heat to heat nearby buildings. There are already many large-scale applications. For example, already in 2010, two Helsinki company established a 2 megawatt data center in underground bomb shelter. Its waste heat can heat 1,500 apartments now. In 2019, IT company Telia built the Nordic country's largest co-location data center in Helsinki. Starting from 2022, energy company Helen has utilized its waste heat to heat over 20,000 dwellings now. Currently, Microsoft plans to build a data center across two cities. The energy company Fortune plans to invest the waste heat, and this is going to be the world's largest data center heat recovery initiative, expecting to provide 40% district heating for both cities and cut CO2 emission by 400,000 tons. Despite applications, this is a typical design of data center waste heat to district heating. It's also applicable to nearby building heatings. Here you can see that the heat pumps are commonly used to cool data center from 15 degree to 10 degree on one hand, and to heat the waste heat to supply to the return line on the other hand. So despite the applications, technical challenges exist. First, the data center's energy density grow dramatically up to 100% growth in average server rack, as shown in the left graph. Therefore, liquid cooling, especially direct-to-chip cooling, are expanding now with very high growth rate also, as shown in this in the right-hand side graph. Second, most data center waste heat recovery methods depend on heat pumps that can consume significant electricity and also very cost. Translating these technical challenges into research gaps, we can conclude that limited research exists on passive data center waste heat recovery without heat pumps. Two critical.
Sorry, there is just this.
It's okay now.
Okay, two critical research issues can be summarized. First, can waste heat from liquid cooling system be fully recovered with just heat exchanger without heat pump? Second, Limited CDU research has focused on primary side waste heat recovery only. Secondary side recovery has been completely neglected. CDU here represent coolant distribution unit or cooling distribution unit that distribute water or coolant in the liquid cooling system. To solve these problems, we introduced a new concept called data furnace through direct-to-chip cooling. The concept is illustrated in the graph on the right-hand side that involve placing distributed or edge data center with a few racks as a data furnace within or near building district heating substations. Here you can see that a few racks can directly heat the buildings as a data furnace. And this way, piping cost and heat loss can be minimized within the building. I want to emphasize that one of the aims of our invention is to simplify piping engineering work at a very low cost. Okay, now I showcase our invention using real data center. This data center called W-Star data center. It is an edge or distributed data center located at our university in the western part of Finland with IT capacity 50 kilowatts, including 30 kilowatts liquid cooling or direct-to-chip cooling. The heated building is an office building that has about 3,000 square meters floor area heated by district heating. The heating demand is about square meter per square meter is 96 kilowatt hour. I demonstrate our solution for W-Star data center using 4 cases. The first is direct-to-chip cooling system without heat recovery, and the second is building space heating network without heat recovery. And these 2 cases are served as base case. Now I propose 2 liquid-to-liquid heat exchanger schemes to recover waste heat from primary or secondary side of CDU. Then I compare the performances. So this is the first case, standard direct-to-chip cooling system as a base case. The middle square represents the CDU heat exchanger. Because we want to be at low cost, so we assume the effectiveness of this heat exchanger is 0.7. So this is an average among commonly used heat exchanger. So this CDU cool the rack on the secondary side and the interface dry cooler on the primary side. And this is the standard building space heating network. TC, here, TC represent control center that adjust this TV1 to regulate district heating flow through this heat exchanger HX1 to supply water temperature at the temperature TE1 according to the control curve shown here or on the right side. So the supply temperature about 45 to 20 degrees. I want to mention that this supply temperature are the regulations in Finland, which could be 20 degrees lower than those in many European countries. Also, I would like to mention that this application is not just limited to district heating. It could be, because here I didn't draw completely, it could be, for example, boiler heated building as commonly used in the UK. And this is our invention, scheme 1, that recover waste heat on the secondary side. It can achieve 100% waste heat recovery. The lower section represent direct-to-chip cooling system, and upper section represent building space heating. The middle square represent our proposed heat exchanger that recover waste heat from the secondary side of CDU to serve the temperature to the space heating at the temperature TE1, according to the regulated control curve that I showed in previous slide, that it is based on the Finnish regulation. The control, the whole system control, it can be realized by two processes. First is TC. This TC regulate waste heat flow here on the secondary side through heat exchanger HX2 to supply the temperature at TE1 according to the Finnish regulation. If the waste heat is not enough, then this TC will activate TV1 that utilize district heating or some other source heat to serve the temperature at TE1 according to the Finnish regulation. This is so this process can be viewed as autonomous or independent waste heat reuse loop. The other control process is through this EIA, and this EIA usually it is shut down. It is activated if and only if the outlet temperature of heat exchanger exceed 41 degrees. Then this EIA will activate the pump here and dry cooler. That's so they only if and only if that. Most of the time, normally this primary side, dry cooler and pump are shut down. So this process, this is for emergency use only, and this can be viewed as waste heat rejection loop. Because it's most of the time shut down, it saves huge electricity for dry cooler and pump. I would like to also mention that the scheme 1 separate the waste heat loop and waste heat rejection loop completely. And this is our invention, scheme 2, that recover waste heat from the primary side. And about 83% waste heat can be recovered. The design is completely quite similar as the first one, except that in the middle, you can see that the heat exchanger recovered the heat, waste heat, from primary side instead of secondary side. So that's the only difference. The control process are the same as scheme 1. But there is a very, very big difference. I think you can discover that the dry cooler and the pump in the primary side must be run all the time. So this is a result. Scheme 1 can utilize waste heat about 150 megawatt hour, equivalent to 71% annual waste heat. Additionally, it can save about 2,291 kilowatt-hour electricity for dry cooler and pump on the primary side. The corresponding values are a bit lower in Scheme 2. We also developed a new relationship graph based on the two schemes, because linear correlation can be found among these waste heat reuse rate, outdoor temperature, as well as space heating supply temperature. Therefore, this graph can be used to aid in designing heat recovery system, or HX2. And there are some new discoveries can be found from the graph. First, Scheme 1 keeps constantly complete waste heat recovery, outperforming Scheme 2. Scheme 2 is this blue line. In Scheme 2, the waste heat recovery decreases as outdoor temperature drops. Second, this is very interesting because we discovered that the slope of the line actually represents the effectiveness of the heat exchanger, with optimal slope being 0 degree as the horizontal line of Scheme 1. Improving the effectiveness of heat exchanger in Scheme 2, for example, by lifting this blue line up, can narrow the performance gap between Scheme 1 and Scheme 2, but the gap can never be eliminated due to the connection differences. In the ideal case, as shown in the horizontal line for Scheme 1, the graph should show no correlation between waste heat recovery rate and outdoor temperature, indicating complete recovery. So these new discoveries can be used to help design and plan energy efficient heat exchangers. So you can adjust it, the effectiveness. Okay, the last session we conducted life cycle cost from a building owner's perspective, because there are many stakeholders involved. So our life cycle analysis is conducted from building owner's perspective. These prices are taken as average or above average values based on online sources. For example, the installation cost typically 15% of the investment based on literature review we consider as 50%. The piping cost is 70 euro per meter, and we consider 50 meters. And also, I would like to mention that because this is the pipe work is within the building, is simple. Because there is no heat pumps, and all pipes are installed within the building, so the investment cost is greatly reduced, under 10,000 euros. And this is a life cycle cost for carbon emission based on the following input parameters. 25 years, this discount rate 7%, inflation 2%, electricity price for the first year 121 euros per megawatt hour, electricity inflation rate 2%, and the district heating price for the first year about 90 euros per megawatt hour with inflation rate 3%. The CO2 emission factor are 89 gram CO2 per kilowatt hour for electricity and 160 gram CO2 emission per kilowatt hour for district heating. And these emission factors are based on the data in Finland or Finnish situation, which I think that may be much lower compared to other European countries. Because in Finland, this electricity is quite clean. Both schemes have payback time less than 1 year and contribute significantly to carbon reduction. Scheme 1 saved over 200,000 euro energy and nearly 300,000 kilos CO2 in district heating, cost over 25 years. The corresponding values are a bit lower in scheme 2. Anyway, nevertheless, both solutions achieve very good result, with 54% for scheme 1 and 48% for scheme 2, compared with the base case. Also, I would like to remind you that these are observed based on a very small single rack, 25 only kilowatts waste heat, and in the cold weather in Finland. Discussion and conclusions. This discussion, this is quite interesting, because initially we thought that full complete recovery of waste heat from data center could be achieved if building heating demand exceed waste heat. But results show very different reality, because you remember that the graph I showed earlier, the scheme 2 is represented by in this blue line, and in scheme 2, the waste heat recovery drops as outdoor temperature drop, meaning that building heating demand increases because the temperature drops. So this is not true. What we thought in the beginning was not true. Conversely, scheme 1 avoids this complicated issue that keeps a constant waste heat recovery rate independent of outdoor temperature. And this crucial finding represents a new insight. For direct-to-chip cooling system and low-temperature space heating, our developed method, scheme 1 and scheme 2, both can achieve very good result. I think one is 100% and the other is 83% recovery, corresponding to 71% and 63% annual recovery. Here I show a reference from the existing literature published in 2020. Because capacities are different, direct comparison is not straightforward. Nevertheless, you can use it as a reference. So this is for simulation result with true waste heat reuse concept based on university-based data center with IT capacity 360 kilowatts. One method is using waste heat to the campus district heating system, and the other one is to heat nearby buildings. Their recoveries are 50% and 20%, respectively. Utilizing waste heat from liquid cooling system without heat pump is highly profitable for space heating, regardless of recovering waste heat from primary or secondary site. And our solution shows that the payback time is less than 1 year. And our outcome, the state-of-art existing, for example, the existing literature published in 2019 for 1,000 kilowatts air-cooled data center analysis with 2 cooling methods. Their payback periods are 10 to 14 years and 15 years, respectively, significantly or much longer than our result. Here are some final takeaways, summarize our solution. So our solutions can achieve complete waste heat recovery in extreme cold weather. There is no need for heat pumps. The cost-effective investment very low, limited to heating pipes and heat exchangers only. And the solution can be applicable beyond district heating, particularly beneficial for 4th generation and 5th generation district heating, especially suitable for low temperature heating systems. And our method achieve a rapid carbon reduction with quick payback time, less than a year. And we can conclude that our method present an affordable, sustainable, and innovative approach to waste heat recovery in data centers. Okay, and this appendix contains some detailed information on the W-Star data center use case, and we are currently procuring equipment with completion in 2025. And this is the office building that where the data center will be located. And these are PVs. And collaboration for joint project applications are welcome. Thank you very much for your attention, and happy Valentine's Day. And I'm happy to answer or discuss any questions you may have.
Many thanks. That's a very exciting research and a really innovative and applied piece of work. We have a question and answer time, 20 minutes. And before we go into through question answers, please feel free to type in any questions you might have in the chat area. So we'll try to answer your questions later on. So I'll type one thing in the chat area. Probably you can type your question there.
Sorry.
Feel free to type your questions. Or if you like to raise your hand, if you would like to ask a question in person, that'd be great. And also later on, we'll publish this recording on CPC website, also on LinkedIn Intelligent Building Group web page. So I just posted a link to the Intelligent Building Group.
Somebody got
Is Tony Aloy, is that correct? Can you just ask a question, please?
Hi, Tonelai from Gran. Great presentation. Just wanted to ask a question about a comment you made there that heat recovery from the data centers doesn't need heat pumps. On a typical 3G network, obviously flow temperatures are going to be 65 plus. How do you envisage we can recover heat into those type of networks at such high flow and return temperatures without a heat pump?
It depends on the return temperature. If it's I didn't catch. You said that the supply temperature,
So flow
recovery
temperatures
is 65.
65, yeah.
Yeah, that's very high, I think.
Yeah.
Yeah, in Finland, as I showed to you, that the secondary recovery, secondary side in district heating or space heating, whatever, is 64, 5 and 30 degrees. So it's plenty of over 20 degree more. In practice, I think no problem. I think you can fully recover that with heat.
Okay, thank you.
Yeah, but even can I comment? Even if not in Finland, because in Finland that is well insulated, and the regulation, I mean that aims for low temperature supply temperature. But I think that normally that the regulated or the supply temperature based on regulation is little bit usually a bit higher. So even if for the old regulation I think it still works if it not recover fully. Thank you.
Thanks.
Okay, thank you. Stephen Parker, please. Thank you.
Hi there. I'm a data center designer, and I've got a question about you said that your analysis was designed on direct chip liquid cooling for a 25 kilowatt rack.
Yeah.
Obviously, data centers that I design, a 25 kilowatt rack is still just a single rack. We have hundreds of racks per data hall. But the direct chip obviously doesn't provide 100% cooling to the liquid. It actually only provides 25 to 30%. It still requires 25 to 30% air cooling, with the remaining going to the liquid. How's that been accounted for in your research?
You mean this air cooled that part?
Yeah. So the direct chip technology relies on putting a cold plate on the chip, but the power supply, the RAM, and the other components within the servers still require air cooling.
You mean the cooling? Well, for example, in our this use case data center, we have this mixed cooling method, both for liquid cooling and also air cooled. I don't get your question. Why you can't use direct to chip cooling? Why you have to use air cool? Yeah,
we do use direct to chip cooling, but direct to chip cooling of a 25 kilowatt rack, direct to chip cooling will only remove 75%, 18, 19 kilowatts of that heat. The other 6, 7 kilowatts will need to be removed by air cooling. Direct to chip cannot take all of the heat out of a server.
Yes, that's true. That's true.
It was a question of whether that's being taken into account into the research.
In the air-cooled data center, no, we didn't consider this air-cooled data center heat recovery. We didn't consider that for with heat recovery. But if you talk about cooling, yes. Or what about the immersion cooling? If direct to chip cooling cannot complete this cooling power or two phase,
yeah. two-phase immersion and single-phase immersion are viable alternatives that will extract 100% of the heat. However, there are concerns over the chemical use and the equipment lifetime in a immersion cooled server. This is why they're not yet widely adopted in data centers.
But I heard that this 3M or that company they said that they promised that they have no chemical problem or for the, let's say that for the air or emission problem. And I heard that they have these two phase that new method that can serve very well. Of course, it's expensive.
Yeah, as far as I'm aware, 3M actually stopped producing two-phase liquid earlier, at the end of last year. They famously launched a press release on it.
Yeah, okay, I understand. Because our work is focused on mainly waste heat recovery. We haven't really considered this air-cooled system. But I don't know in UK, in Finland, this air-cooled system can reach the temperature about 45 degrees. It can be, maybe it can be also used in floor heating buildings.
Don't take me wrong. I'm not meant to be negative to the research. It's good research, and actually we're adopting a very similar approach to heat export from our own data centers. In fact, we're looking at a 20 megawatt heat rejection to a local heat network using just a plate heat exchanger. So it's absolutely the right thing to do. But I would just say that there needs to be a lot more detail added. But I'm happy to facilitate that and get that message across to other data centers.
Okay, thank you.
Thank you. Very good question, excellent answers. We have 3 questions on the chat area. Professor Lu, probably you can see the chat area. The first question is Mohammed.
Sorry.
Okay, I'll read it out. What type of heating system have been considered for the building? So it's for the building for heating. Is that what you're asking?
Talking about, if we talk about the waste heat recovery, any heating system, anyone can be utilized. The only requirement is the return temperature should be, let's say, because this supply temperature about 60. So in practical point of view, it should be maybe 20 degrees lower. Or in theory, 10 degrees, okay. But I mean, if we talk about practical things, you never know this 10 degrees. So it should be 45, 40 degrees, okay. So any heating system build and work around heat recovery for air-cooled rack. And I'll show it. I haven't done, I just know I mentioned to the previous answer, I haven't done the air-cooled recovery system. But I don't see the difference. The only challenge is that the air-cooled work, the supply temperature is lower. But perhaps you can use to lower heating system, such as, let's say that floor heating buildings, that maybe 30 degrees is okay. Or maybe ventilation system. But I think in principle, it's the same.
Yeah, thank you. Next question is from David Bassett. I think similar to Stephen's question. Have you done any work around heat recovery from air-cooled only racks and associated UPS supporting those racks?
No. But I think that I mentioned that in principle, I don't see the difference. It's only that the air-cooled system comes be lower temperature, but you can use in a lower heating system like floor heating buildings. So or maybe ventilation system, it has lower temperature, so there's no difference.
The next question is from Lagos. What are the recovered temperature in your system?
In the liquid system, it's 60 degree.
60 degree.
About.
Okay.
And but it's different in the secondary recovery system. It's about in the scheme 1, it is 60 degree. But in the if you recover from primary system, it's 50 something.
Thank you. Are there any other questions? I think that is all question we have in the chat area. As you mentioned, is Finland and UK, we might have different insulation and regulation on heating systems. So there's a public consultation on district heating. So feel free to response. So we'll post that consultation in the entire building group if you're interested.
But I have one interesting question for you for UK, but because you normally you use boiler to heat the building. Yeah. What is the return temperature if you use boiler?
Anyone
typically
in
boilers.
In UK.
Yeah, we normally flow and return in peak winter about 70, and then coming back, it's 60. We're trying to push down to 75, 55 on newer buildings. Older buildings can be 80, 70 sometimes. So it varies on boiler design. We're not very good technically about managing delta T's across building. So it's quite varied depending on which building you go to. But we are trying to push for condensing boilers to be lower. And then with heat pumps, obviously that's dropping a bit further.
Okay, thank you. So it's much higher than Finnish, than the return temperature in Finland.
You'll be monitoring some radiator temperature in some buildings. It's really varied depending different room insulation conditions. It's very wide. Sometimes probably 45 to 65. So it's quite different in different settings. But thank you. Next question. Will the attendee list be shared? I don't think, Dundee, that will be shared. I don't have the list. I can ask CPC, but usually we don't share the attendees list. Feel free to post any event. So if you like to promote through our social media, LinkedIn web page, so I post that in the chat area later on. Next question: what is the practical distance over which it is possible to export the heat before capex begins to become too high?
What do you mean this practical distance? Is it physical distance?
Yeah. Do you want to clarify?
Yeah.
Your rapport, Mohammed? What do you mean by practical distance?
I can answer this way because the major cost is this piping. I think heat exchangers are not very expensive, so that's why we propose that we propose that these racks are not very far from these buildings. But in Finland, it's per meter cost 70 euros. So then you can calculate that. I think that it can't be if it's very, very far for standalone data center, then our method doesn't work for that because it's too expensive.
Austin, I saw you raise the hand. Do you like to ask a question in person, please? You have to unmute yourself first, please. Austin Williams.
Austin Williamson. Yep. That's getting a bit of feedback. Apologies. Thanks for the presentation. Has any consideration been given to the size of the distribution pipework and the terminations to the DH substation? This particularly relates to the larger data center buildings.
Sorry.
Carry on. Apologies.
Yeah, sorry. I think I mentioned that this our work. One of this innovation is this pipe work is very simple. It's just because for the substation building, you just link to the secondary side. It is very simple. But if it's a very big data center, I don't think it's depend on the size of the data center, but the distance to the space heating.
Yes.
Space heat. Yeah. If it's very, very long, very far, then it doesn't work because the piping, as you can imagine, is too complicated and expensive.
Yes. Okay. I was just making the point in relation to the real estate of the and getting the pipe work out of the main data halls. But yes, thank you very much for that. For that response. Answer. Thank you.
Okay, thank you. Any other questions? I saw this question: will the slide deck be shared with attendees? We will publish the recorded video. Whether the presentation slides will depending on Professor Lu, whether you would like to share or probably I'll ask Professor Lu if you like to share or not later on. Okay, any other questions, guys?
You can start distribute energy content focus on low heat. You're looking for a partner. Thank you.
Yeah. Yeah, I know in the audience there are some district heating kind of broker, not probably direct supplier, but they might be able to help.
Yeah. And I also want to mention that this is passive heat recovery. So yes, it's not yeah.
Okay. Right. Okay. So yeah, Golden replied. That's great. So happy to hear more from you, Golden. Okay. Many thanks. I think that is wonderful, and look forward to see you guys again.
Thank you very much. Thank you.
Bye bye. Thank you. Bye bye.
Bye bye.
Bye.
Thank you.
Bye bye.
Bye.
Thank you.